Today we will be presenting our findings on the ME 4056 Week 1 Refrigeration Lab. Presenting today is Group 1, and we are Isaac, Nate, Jasmine, and Andrew. This is the honor code, and we followed it. And now getting right into it. This is a layout of our goal and purpose for conducting this experiment. We want to model the refrigeration system and determine the cooling system's capabilities for the purpose of characterizing specific vortex tube relationships. So this is going to be between the input pressure at sensor 3 and various other parameters such as T4C, MC, T4H, and MH, which is pretty much just the temperature and mass flow rate at the cold and hot inlets. So then we want to characterize the heat and energy transfer at the aluminum block. So this involves calculating the thermal resistance of the insulation as well as calculating the effective mass, and both will be compared to known values. So our methods for data collection. We didn't get too involved with this process just because, virtual lab, but I just want to kind of go over the purpose of each station just because it kind of, develops a schematic and tells you exactly what data we are working with. So at station 1, we're going to be measuring the temperature and pressure values of compressed air, and on the way to station 2, it's going to cool the temperatures down to ambient temperature. So at station 2, we should have those values, and then on the way to 3, we're going to remove rapid pressure variations from this compressed air. And then at station 3, we should have very good data of stable air pressure and ambient temperature. And then it's going to split in the vortex tube. So at 4H, we'll be reading elevated temperatures and flow rate, as well as on the cold side, we're going to flow this air over the aluminum block, and we're going to be measuring air temp, pressure, and mass flow at station 5. So then in order to process this data, we're going to initially plot these values in order to determine these key steady state values. We're going to use linear regression using York-Fit so that we can develop these equations that relate these various parameters and develop the system cooling equation. And then we're going to be using energy balance and heat transfer principles to calculate the thermal resistance of the insulation and effective mass of the aluminum block. So now to discuss. So this is the vortex tube analysis at steady state. So initially we plotted P3 with time in order to kind of get a good steady state value, and we noticed that there was a drift pressure that we subtracted or corrected for from the other 4 values, and that resulted in the vector shown in the second bullet. The different colors represent the amount of data that was used in order to calculate the steady state. So in this case, there was a lot of data to work with because it looks similar to a unit function. Not similar to that, for the steady state temperatures at the cold and hot inlet at sensor 4, we actually had very little data to work with because it converged very last minute to its steady state temperatures, and it can be seen that the trend with the sensor 3 pressure is that at the cold outlet, the temperature would decrease with increasing pressure, and for the hot, it would increase with increasing pressure. This is the steady state for the volumetric flow rates. You can see that we had a lot of data to work with in order to calculate the steady state values, but you can see that both increase with increasing pressure at sensor 3.
Now, moving forward with the data that we found in the steady state section, putting it through a log-log format change and then through a York analysis, we managed to get these plots which indicate general trends that as inlet pressure increases, the mass flow rate increases and the cold temperature decreases. Now, next slide, the hot temperature increases and the mass flow rate increases.
We are given this system cooling equation and are told to find the parameters tau and B. XO is the starting temperature, XSS is the steady state temperature, and XT is the temperature at time t. By taking the natural log of this, we can fit it using a York regression, and it becomes linear. Our Y is the difference between the steady state temperature and the turn temperature. Our X is the time, and our slope is determined from the York regression to determine the tau, and same with our intercept to determine the B. We got the tau of 800 with a high uncertainty due to the lack of data given, and it had a cooling time of roughly 2,250 seconds. For 80 psi, it is about half of the tau from the previous one, which corresponds to a cooling time of only 1,200 seconds. which means twice as much heat transfer occurred.
Now we will be calculating thermal resistance. We will do this using an energy balance of the heat transfer to the air equals the heat transfer to the ambient surroundings plus the heat transfer to the mass. We can simplify that equation to Q dot air equals Q dot am because the change in temperature in steady state is 0, and therefore the Q dot mass term will drop out. Our values are listed on the slide, and as you can see, our theoretical value is much higher than the two pressure values calculated. This could be due to a couple of factors. The first being that the lumped mass model may not actually be valid here, and that is because of the large amount of time of the experiment to take place. That is assuming that all the heat transfer is happening within the mass much more rapidly than it is through the insulation, and that might not be the case. Furthermore, we calculated the Kns values also listed on the slide, and those seem to be much higher than the 0.033 value given for styrofoam. So we can maybe say that our insulation was a different material than just styrofoam. Finally, the top of the block was not insulated for the experiment, and our theoretical value assumes that all of the surface area of the mass is perfectly covered up by the insulation for the calculation. Similarly to thermal resistance, the effective mass can be calculated using Q dot air equals Q dot mass, as the Q dot am term drops out to the lumped mass model. As you can see, our values are on the slide, and they are close to the measured mass, but there is a little bit of a discrepancy there. So the first reason for that could be that the volumetric flow rate is not scaled to temperature and pressure. Furthermore, 900 was given to us as the aluminum specific heat, but we were not sure if our block was precisely aluminum. Also, we had to choose data ourselves for the partial t, partial time term, and we chose the beginning of the data with the steepest slope to represent the most physical characteristic of the heat transfer. Finally, the data was not collected for the first 500 seconds for the 50 psi data, so there could be some behavior there that we are not capturing.
So key takeaways. We found is that as pressure increases, it has several effects on the vortex tube. As inlet pressure increases, the outlet mass flow rate increases out of both ends, and the hot temperature increases and the cold temperature decreases. Now all of this increases the heat transfer at the mass. And another thing we might want to consider is that some of our assumptions starting out might need some revisiting as we move forward. Now, here's our code. Any questions?